Let's talk about the 8.1 and eventually 8.2, but it takes time. We're not going to do all of them. So what we would like to do, we'd like to solve a system of, solving systems of linear equation, of linear first order. First order differential equation. First order differential equation. So this is going to be our job. Of course, one way to do it is just a Laplace transform, and then you decide the other way. It takes time, but this method is much, much easier. So we are going to review the matrices first. Whatever we need, we're going to introduce it, then we come back and we change it to the, we change it to the differential equation. There you are. So review introduction to the matrices. Just a brief one, introduction to whatever we need. Matrices. You know the notation of a matrix. So if A is equal to the Aij, the entries of a matrix, for I, it's going to be just 1 and 2, but I write the first one in general form, equal to the 1, 2, 3 up to the M, and J is going to be equal to the 1, 2, 3 up to the N, is going to be, is any, no, it's going to be a function or any array, or rectangular array, any array of numbers or functions. It's not going to be numbers all the time because we are going to change it to the functions. So you know that the A is going to be in general. It's going to be a matrix, so it's going to be A11, A12, up to the A1N. Then you continue the other ones. It's going to be A21, and at the end you get the AM1, and then you continue. This is going to be A22 up to the A2, N, and you can write all the other entries, and you get to the AMN. So this is going to be, this is going to be A is, A is going to be an M by N matrix. If M is equal to the N and is equal to 2, I go to the 2 by 2 right away. Then in this section or chapter, we are going to have this matrix, A11, A12, and this is going to be A21, A22. This is going to be a 2 by 2 matrix. This is it. We quickly change it to the what we need. We don't need any higher dimension, if you like, or size. So the operation that we are going to have. So for example, if I write the A equal to the -2, 3, 5, and -7, this is going to be a 2 by 2 matrix. Then I need to show the solutions in this form. And if I write the vector X as 1 and -2, this is a 2 by 2 matrix. 2 by 2 matrix called, a column matrix. A column matrix. Because we are going to have a solution set as a vector. Is going to be as a vector, and then we are going to denote it by these forms. Okay, just this one so that we can see the better format of this one. Okay, you see it. So that would be better. Okay. Now, operation that we need to know how we're going to define two metrics to be equal to each other. So equality of matrices. Two matrices are going to be the same if they have the same entry. Okay. So we need this one. So two matrices, A and B, okay, are equal if the corresponding terms are going to be the same. So if Aij is equal to the Bij, in this case, I and J can be just 1 and 2. It's a 2 by 2. So this is equality. Then operation that we are going to use, if you want to multiply by a number, so multiplies, okay, multiplies of matrix. If you want to multiply by a constant, you multiply all the entries, okay? So this is the case. If you want to multiply K times A, you simply multiply each entry by K. KA1, 1, KA1, 2, and it's going to be KA2, 1, and the KA2, 2. We need this one. So for example, if you multiply 5 times, if you want to multiply 5 times this matrix, it's going to be 2, -1, 4, -2. Multiply the 5 by each component or entry. So 5 times 2 would be 10, -5, 20, and the -10. Okay, so that would be the multiple of a matrix. Any question? We are going to, of course, dealing with the functions. So when you're dealing with the function number 2, you may like to multiply the function e to the t times a column vector of 1 and -2. So we multiply each entry by e to the t. So that gives you e to the t, and this is going to be -2e to the t. Okay, so this is the way we're going to operate. Or we may do it from a different direction. So the different direction would be if you want to multiply 2/5 as a column matrix, you multiply by e to the -3t. So this is the way we're going to write it down. It's going to be 2e to the -3t, and this is going to be 5e to the -3t. Okay, so be prepared for it. Because the solution of that eventually equation are going to be of this form that we're going to have. Okay, so this is a scalar multiplication, if you like. You multiply by a number. Any question? No addition and multiplication. You need to go up to the eigenvalues if you are familiar with these terms. So this is a scalar multiplication with different form. Now, if you want to add, there are going to be a 2 by 2 matrix, so nothing to worry about. You can add it. Okay. So addition of a matrix, matrices, addition. Okay, addition of matrices. You just add them, term by term. I'll just give you an example, or you can write it down. You have 2 matrix. Okay, suppose A and B, again, are going to be 2 by 2 matrices. Then if you want to add, you add the corresponding terms together. So A plus B would be simply AIJ plus BIJ. Or again, I and J equal to the 1 and 2 on. In the case that we're going to have just a 2 by 2. We need this one too. So example. So if A is the matrix 2, -1, 0, 4, and B is going to be 4, 7, 9, and 3. If you want to add them together, you add the corresponding integers. Okay, if this is going to be the case, then you have A plus B equal to, you add the corresponding integers, so it's going to be 2 plus 4. And this would be -1 plus 7. And this is going to be 0 plus 9. And the 4 plus 3. So the new matrix is going to be 6. Okay, 6, 9, and 7. So this is the addition. Our square matrices, we can add them nicely together. Next, we need multiplication quite a lot. Okay, multiplication of matrices. Multiplication of matrices. That is different, you know, the matrix is a function. So if you want to multiply it, you have to find the composition of the function. So the composition would be of this format. Okay, so this is the way we do it. A times B is the matrix A11, A12, A21, A22. We multiply by another one, which is going to be B11, B12, B21, and the B22. You know that the way we multiply it is it's kind of a dot product. You take this one, you multiply as a dot product by this one, and then we come back. So the result is going to be a new matrix. So if you multiply this one as a dot product, you get this one, A11, B11 plus A12, B21. That's a pairs. We continue the second one. So that gives you A11, okay, B12 plus A12, B22. Okay, so multiply the first row by the other column. And then we come back and we do the second part. Okay, we do the same thing for this one. So you are going to get the A21, B11 plus A22, B21. And you do the last one. So that gives you A21, B12 plus A22, B22. It's easier than it seems to be, you know that. Because when we get to that last part, when we get to the non-homogeneous, we do this type of things quite a lot. Okay, so example. Yes. You just get this vector, you multiply by this vector as a dot product. The dot product. Then you come back, the red one, multiply by this vector, dot product. You know that the dot product will just multiply the coefficients together. Okay. So give you an example, see how we're going to operate. Example, suppose you have the following, A equal to 4, 7, 3, 5, and the other one is B equal to 9, -2, 6, 8. So we're going to multiply them together. Okay, are you ready? Solution. What is going to be A times B? You get this row multiplied by the other one. So it's going to be equal to 4 times 9. 4 times 9, 36. Plus 7 times, okay, 7 times 6. 42. Then you continue 4 times 7 times the second row. 4 times -2 would be -8. 7 times 8 would be, yeah, I'm sorry, I have to go forward. So I multiply this one to get this, okay. Then I multiply, go forward, I write it down here. It's going to be -8. Okay, it's going to be -8 plus 56. That's the first one. Okay, that's going to be, you take this one, and then you continue to get the other two. Then you come back in the second one, and you do the same thing. 3 times 9 would be 27. Okay, 27, 5 times 6, 30. Then you come back and continue. 3 times -2 would be -6. And the 5 times 8 would be 40. So the final answer, 36 and the 42, that gives 78. Okay, -8 to 56, that gives you 48. 27 and 30, that give you 57. Okay, and that make it into the 34. So that would be the product of the two matrices for the 2 by 2. The one that we need is very special. We multiply a vector by a matrix. This is what we need. Any question? This is what you need to do this one most of the time. Because there is going to be a solution vector, we call it, and A is going to be, we call the matrix of the coefficient. So there you are. The second one, X, is a column vector. It's a -1 and 2. And then we would like to find what is going to be. Okay, if this is given to you, you have to find the A times X. Then you want to do the actual equation. So this is it. This is going to be your A is 4, 7, 3, 5. It's a 2 by 2 matrix. And then you multiply by -1 and 2. You see, this is a 2 by 2. And this is going to be 2 by 1. So you know that the result is going to be 2 by 1. So this is the result. You get the first column, you multiply first row, -1 plus, -4 plus 14. You're done. The second one, 3, 5, -1, 2 is going to be -3 plus 10. So the top would be 10 and the bottom one would be 7. So this is the way you multiply a column vector by a matrix. And you need this one when you go to the multiplications or to solving the equation. Okay, so that's a multiplication. We need to make sure that we remember the so-called multiplicative identity. What's the stand for 1, if you like, for the matrices. Okay, so the next thing is what is multiplicative identity matrix. Just a notation to make sure you remember it. You are going to use this one quite a lot. So multiplicative identity matrix. So we denote this one by I, and the I would be 1001. And the property of I is like, when you multiply by any other number or any other matrix, it's going to be identical. Means A times I is equal to the I times A, and it's equal to the A all the time. So for any matrix, when you multiply it, you get this result. It would be important for us when we want to design the solution of that differential equations that we need. Any question? A couple of more terms, and that will take us close to the differential equation. Now, the next thing that we need, that we are going to use quite a lot, is the notion of the determinant. Okay, for the 2 by 2, it's very easy, so we don't need to talk about it in full details. Okay, are you ready? Going to the next page and get the determinant of a square matrix. We just focus on the 2 by 2. Nothing else. Okay, there you are. So what is going to be determinant? Okay, determinant of a square matrix. It's just a 2 by 2 that we are interested in. So there you are. If A is equal to the 2 by 2, A11, A12, A21, A22, then the determinant of this, okay, then the determinant. Okay, determinant of A is denoted. Okay, denoted by. There are two different notation. You can use the straight vertical line if you like the absolute value. If you write your matrix with this notation rather than the parenthesis type, this means you are talking about determinant. But we usually use the most convenient one, that of A. Okay, I use the second one. For the first one, when I have the matrix, but when I write it down, I use the second one. Okay, and it's going to be defined by, it is a function again. And it's going to be defined by, that's it, the determinant of the A. It's like a cross multiplication that give you A11, A22 minus the other way around. A21 times A12. Make sure the order is as is. Okay, A11 is cross multiply. A11 times A22 minus A21 times A12. That would be the determinant of a matrix. We need this one. We have to use it for all the problems that we are going to do. I'll give you one example. So if your matrix is going to be this, suppose A is equal to 3, 6, okay, 2, 5. Then the determinant of the matrix, if you use this notation around the matrix, this means you're talking about determinant. Okay, cross multiply is going to be 3 times 5 minus 2 times 6. 3 times 5, 15 minus 12, which is equal to 3. Okay. So that give you is equal to 3. So the determinant of your matrix is 3. Determinant of A is equal to 3. Okay, there are some property of the determinant, but we don't need it, so we're not going to talk about it. Okay, that we can talk about it quite a lot. So that would be the determinant of the matrix. Any question? Now, most of the matrices that we're going to use are going to be matrix of functions. If it's going to be a matrix of functions, then we may have to differentiate it. So if you want to differentiate the matrix of the function, you just differentiate each entries. Or sometimes you may have to integrate it. So we integrate each term one by one. Okay, so we do a calculus of these. So what is going to be derivative? Okay, derivative of a matrix of function, of a function matrix, of a matrix of functions. The functions are going to be functions of time. So we denote them by f of t, g of t. Okay. So basically, this is it. If your matrix is going to be matrix of function, it's going to be a of t. So a of t are going to be each term, a, I, j are going to be a function of t. So is a matrix is going to be is a matrix whose entries are differentiable function. Are differentiable function. Okay, there are going to be differentiable functions, then you can differentiate it. Then the derivative of your function or matrix form is going to be a prime of t, differentiate respect to the t. So we differentiate each entries. So it's going to be a prime of the aij t. Okay, so this is going to be derivative of a matrix of function. Similarly, you can get integration. If you can do the derivative, we are not going to get the integral, but we just remind you. So if you want to find the integral, for example, from t0 to t of a matrix, let's call it ASDS. So we just integrated each entries. So the result is going to be a matrix, but the entries of the matrix is going to be the integral of a t0 to t, okay, aij of the s ds. So basically, if you want to integrate the matrix, you integrate each entries. If you want to differentiate it, you differentiate each term. So the result, again, is going to be a matrix. We need the differentiation to do it. Okay, I'll give you the example. It's just the one that actually we are going to use. So example, for the differentiation, you differentiate the solution of your system, okay, of the equation that we're going to have. Solution is going to be a vector, a column vector, if you like. So if x of t is going to be a vector, but is a vector is going to be column vector. And the first row is going to be the sign of the 2t. And the second one is e to the 3t. You see, this is going to be a matrix. So this is going to be, solution of a differential equation, and you want to check it. So we have to differentiate it. If this is going to be the case, so if you would like to find the x prime to confirm or to check to see if the x of t is the solution of a differential equation, so we differentiate each entries. Okay, for example, the first one is the sine of the 2t, so just find the derivative of the sine of the 2t. So it's going to be 2 cosine of the 2t. That's the derivative of the first entry, and the derivative of the second one is the exponential function, never change, but you have to multiply by your prime, so it's going to be 3e to the 3t. So that would be the derivative of the column, okay, of the column vector. Because that the coefficient are going to be constant in the one that we're going to do. So only the variable part is going to be the vector solution. Because, okay, that's one. You're not going to integrate, but I'll just give you one example. Yes, to know it. So for example, if again, x of t is going to be a column vector of this form, it's e to the 3t, but 8t minus 1. And you would like to integrate it. antiderivative, if you like. So in this case, the integral from 0 to t, x of s ds. Since we use the t, so in the differential, we call it s. You can call it anything you like, doesn't matter. Okay, so this is going to be equal to, so you integrate each one of these entries. So you know that integral of e to the negative 3t would be e to the negative 3t, but you have to divide it by u prime. So that gives you 1/3 e to the 3s, if you like, but the s going from 0 to t. We differentiate the entries. And the second one, you integrate 8t, that gives you 8t squared divided by 2 minus t, sorry, minus s, it must be s. It's going to be the same thing. 8s squared minus s, then from 0 to t. So if you substitute the first one, if you put the t, that give you 1/3 e to the 3t minus, if you put the 0, that give you 1/3, because e to the 0 is 1. But for the second one, so if you substitute t, 8 over 2 would be 4, so that give you 4t squared. 4t squared minus t. So that give you the result. Okay, no, I'm not going to integrate the differential. So this is all we need to be able to get through our equation. Okay, so what you are going to do, a system of differential equation will be given to us. We're going to change it into the so-called matrix form. We change it to the matrix form, is like the ordinary equation that we did at the beginning of the course. Then we can take care of it. Of course, we change it into the format of the operator equation or the linear equation. Okay, so let's say I'm going to change a system of the differential equation into matrix form. This is your first job. When the system will be given, you have to change it. Okay, any questions? So these are the preliminaries. Now we are ready to give the actual one. So this is the way your first step for solving the system of the equation. Okay, so example. We'd like you to write each system of the equation as a matrix form, as a matrix equation. So write, write the given system, write the given system, the system of differential equation. I would like you to write it down in matrix form. Okay, write it in matrix form. In matrix form. This is it, the first one. This is the equation that we have, system that we have. dx dt, or x prime, is equal to the 3x minus 5y. And the second one is dy dt is equal to the 4x plus 8y. You see, this is the way we're going to change it. We're going to introduce so-called, we call it the solution vector. The solution vector, you have the unknown are going to be x of t and y of t, because you have the x prime and the y prime. So this is the way you're going to organize it. You are going to suppose, okay, you're going to suppose x of t or x, it doesn't matter, x of t is going to be, this is going to be x of t, y of t. Okay, or in short, this is going to be a column vector, x, y. We suppose this is going to be your solution. Okay, so this is the solution vector, we call it. Solution vector. If this is going to be solution vector, then, Okay, then your x prime is going to be what? So your x prime of t, or just the x prime, is going to be what? It's going to be x prime and y prime. Is the case? Then the other one that you are consider going to be function, we call it the matrix of the coefficients. So the next one, the matrix of coefficient. Okay, is going to be, is defined by, or we can define it. The notation that we use A for the matrix, and the coefficient are going to be coefficient of this linear equation. So this is going to be 3, -5, 4, 8. Okay, you pick the x to be xy or x of t, y of t, and the a to be 3, -5, 4, 8. Now, if you change the system, what are you going to have? If this is going to be the case, then you are going to have, you see this dx dt, dy dt is x prime, y prime. So that would be denoted by x prime. X prime equal to the matrix, okay, matrix of the coefficient. You see, this is what you get. You get 3, -5, 4, 8, times it by x, which is the same as, or x prime equal to the a times x. If you multiply them together, you will see it. You see that, you know, just for your information, note that. You see, if you check this one, if you check your a times x, that gives us simply 3, -5, 4, 8 times x, which is xy. So if you multiply them together, you see, remember, the way we multiply 3 times x, that gives you 3 times x minus 5y, and that gives you 4 times x plus 8y. Okay, so that would be exactly what you have over here. Okay, so this is it, and the x prime is simply what? It's going to be x prime, y prime. So we get exactly what you have in the given equation. So that's going to be 3x minus 5y, and that would be 4x plus 8y. So this is the way you quickly change the system into this is a matrix form, x prime equal to the ax. You have done linear algebra, you know the rest. It's a linear equation, okay, and you get the solution right away in terms of the eigenvalues, but we are going to prove it for you and talk about it. So anytime the system would be given to you, quickly change it to the matrix form. Matrix form, then your next job, you will see, your next job is to work on the A. When you form it, from now on, it's just going to be algebra. Nothing to do with the differential equation, okay, for the rest of the problem. Okay, so that's a type 1. Any question? So quickly we change this format. Okay, we understand it. If you write it in this form, don't have to prove anything. You can write it in this form or the other one. We accept both of them when we do the problem. We start solving the equation. This is a type 1. This is called homogeneous. It's called homogeneous because there is not extra things here. Remember, this is it. X prime equal to the ax. It's like it's a linear differential equation. Okay, there is no constant term, if you like. So this is the homogeneous one. Now, you may be given non-homogeneous. We are going to solve both of them. So let's give you one with the non-homogeneous. So that was number 1. Number 2, check this one. We wanted to change this system for us. So this is the system. You have the dx dt is equal to -3x plus 4y plus e to the negative t sine of the 2t. You see, I have an extra term. And the second one, you have dy dt to be equal to the 5x plus 9y plus 4e to the negative t cosine of the 2t. So you see this part is homogeneous. This part is homogeneous, but you have to introduce a new vector. A new vector for the non-homogeneous part. It's the one we call it R of X, G of X, remember previously. So quickly, if you want to change it to the matrix form, these two would be changed into the X prime equal to, then matrix of the coefficient, matrix of a coefficient, -3, 4, -3, 4, 5, 9. This is the matrix of coefficient. And you have extra term now. You have extra term, you have to introduce a new column vector. So the new one is going to be, you get a column vector. The first part is going to be e to the -t sine of the 2t. Okay, and the second part would be 4e to the -t cosine of the 2t. So this is going to be a matrix form. Okay, I missed something over here, and this must be an x here, remember? An x here, because when you multiply them together, that should give you -3x plus 4y over the 5x plus 9y. Okay, sometimes we write this one in brief form. This is fine. But in the brief form, you have to introduce a notation. So sometimes they call this one A, and they call this one f of t. Okay, or just A of t or B of t. So x prime is equal to the ax plus f of t. Let me understand what we are talking about. Okay, but you know, this is fine. Because you just want to give a matrix form. Okay, so be prepared for it. You know, both of them would be given to you, and you are going to solve both of these. At the end of this chapter, you should be able to solve both of them. Okay, the first one and the second one. It's like the one that you did for the differential equation before. We have to solve the homogeneous one first, then we come back and we do the non-homogeneous one, depends on the method that we're going to apply. Yes.
So you don't want us to give an answer in terms of the determinants, you just want this.
No, in this one, this is just the beginning.
Oh.
It's just changing into the matrix form, the beginning. Okay, step one. That we are going to get later. We just want to get to know it, the new format, then we go for it. Okay, one more thing to go. So, you know, like the one that we did before, a function, remember a function was given to you and they asked you to prove that this is going to be the solution of the equation. You just substitute, you get the solution of the equation. It's the same thing. So if you see these type of problems in your assignment, so don't be surprised. So just give you one of them. You know what we are talking about? Okay, of course, we are going to solve the equation, not verify. In this problem, they ask you to verify. Okay, we want to verify that the vector, the given vector, the vector x is a solution of the given system, of the given system. Okay, so a vector and a function is given, and you've been asked to confirm it. Okay, so this is it. Just do one. So this is the system. The system is dx dt. Okay, dx dt equal to the 3x minus 4y. Then the dy dt, the second equation, is the 4x minus 7y. And they give you this vector, x equal to 1, 2. Okay, 1, 2 times e to the -5t. We want to prove that this is going to be the solution of this system. Okay? We have to substitute. You can change it to the linear form, that would be easier, and then you get the result. Okay, so the solution is going to be, you can change it to the linear system. So this is going to be x equal to the, okay, this is going to be x. The coefficient matrix is a 3, -4, 4, 7, that is x prime. You have to prove this one. Okay, x prime equal to the 3, negative 4, 4, negative 7 times the x. Okay, so you need to find the x prime. You better multiply e to the negative 5t inside, then differentiate it. So it's going to be x equal to, look at this one. I rewrite it as e to the negative 5t, then 2e to the negative 5t. Now differentiate it, you get the x prime. So the x prime is going to be derivative of the first one is a negative 5e to the negative 5t. And the derivative of the second one is a negative 5 times 2, negative 10 e to the negative 5t. Okay, that's x prime. You have to prove that a times x is going to be equal to the x prime. So find the other part. This is it. You have the 3, negative 4, 4, 7 times x. Negative 7. That is negative 7. Yes, negative 7. Okay, times x. So this is going to be 3, negative 4, 4, negative 7 times it by x. X is the given vector. It's e to the negative 5t and the 2e to the negative 5t, multiply them together. Remember the way we talk about it? That's going to be equal to what? 3 times that give it 3 e to the negative 5t minus 8 e to the negative 5t. So 3, negative 4, dot product by the others. In the second part, it's a 4 times 2 would be 8. Okay, that give you 8 e to the, sorry, you're going to be 4, the first one. It's going to be 4 e to the negative 5t, and this would be minus 14 e to the negative 5t. Simplify it. So the top give you negative 5 e to the negative 5t, and the bottom one give you negative 10 e to the negative 5t. As you can see, all of them are the same. So that's ax is equal to the, and this is going to be x prime. So we prove that yes, x prime equal to the a times x, and x is the solution of the system. X is the solution. The solution of the, okay, of the system. So we have some in your book. So when you do it, this is the way you're going to verify that the solution is what the claim is the case. Okay, any question? Now, one more step. Now, how we're going to solve that when we change it to the, okay, when we change it to the x prime equal to the ax, how we're going to solve this equation. Okay, now we need one more thing to be able to do it, and this is the notion of the eigenvalues. So we're going to introduce the notion of the eigenvalues, then it would help us to be able to solve the equation. Okay, so let's see what's going to be the eigenvalues and eigenvector of a given matrix. Quite interesting concept from linear algebra, but we need only the case of the 2 by 2, so you'll be able to do it right away. Okay, so this is it. What is eigenvalues? Okay, that's it. Eigenvalues and eigenvectors. That's your main job, to find these quantities. Vectors. You know that the way we are going to define this one in linear algebra, if a matrix is given to you, matrix is going to be a collection of, okay, a collection is a function. It's going to be a collection of actions. So if you apply this collection of the axes on the given vector, and you find out that eventually the result is going to be a scalar multiple of that vector, that's very good. This means you do some operation and you get back to where you started. If you can do this one, that vector is going to be called eigenvectors. And if it's going to be a multiple of that vector, that's going to be called eigenvalues. It's quite interesting. The most interesting application of the eigenvalues and eigenvector is the Google search machine. So when you Google something, you know that. It's open up the windows for you. Those windows, you're looking for the eigenvalues. As soon as you get the eigenvalues, and at the end, they list the information for you. Down, down, down. Of course, you know that finding those eigenvalues, eigenvectors are very difficult. And for years, Google keep the secret that because there's going to be an equation, they have to solve it. So that equation was huge. So it was a secret that how they do this type of equation. And eventually, you know, I think the guy is Larry Page, I think is the one, the co-founder of the Google. He was the inventor of that equation. But today, everybody knows that. Okay. Solving that equation. So they didn't give us the method of how they solve that equation. That was their money. So they're not going to give it away. No, at the beginning was, you know, the case. But later on, you know, that different system comes up and different people they do it. But they did a great job. They make lots of money. So they're not going to give it away right away. Okay, but you know, today we know it. So there you are. So that's the best application of the eigenvalues. But if you study, you know, linear algebra, there are quite a lot that you can do with eigenvalues, rather than the Google search machine. Okay, so it's a foundation of quantum mechanics, etc. Okay, let's do it with the 2 by 2. Just restricted to the 2 by 2. So there you are. Let A be a 2 by 2 matrix. Be a 2 by 2 matrix. That's it. A number. It's a scalar number. We call it lambda. Okay, is set to be. Okay, it's set to be an eigenvalues. You know, the eigenvalues is a German expression, means a proper value. Okay, to be an eigenvalue of A, if you can find a non-zero vector, if there is a non-zero vector K, it's going to be a vector. So the notation is this one. I use the uppercase K for the vector, but I use the lowercase for the components, K1 and K2. Okay, A be a 2 by 2 matrix, and number lambda is set to be an eigenvalue of A if there is a non-zero vector K satisfying, okay, such that A of K, okay, that's it, AK is going to be equal to the lambda K. So this means, you know, you got this vector, then the operation that you're doing with the matrix would be just simply a scalar multiple of K. So if this is going to be the case, then K is going to be called, okay, this, we call it the solution vector. The solution vector that satisfies this condition, of course. Solution vector K is going to be called the eigenvector. Is set to be, okay, an eigenvector. Eigenvector corresponding to that value of lambda. Okay, corresponding to the eigenvalues. To the eigenvalue lambda. So for each lambda, we can find at least 1K. If you find one, then there are many, many, of course. Okay. So we do a little bit of algebra in this equation to see how we can find it, how we can solve it. Okay, and getting some help from linear algebra. You see, note that. if you want to simplify this equation, AK is a lambda K. You see A is a matrix and the K is a vector. It's just a kind of multiplication with K. Okay, so you can move everything to one side. It's like an equation. Remember, the K is the unknown. It's minus lambda K is equal to the 0. We can factor out the K, but you got to be careful when you factor it out. So it's going to be A minus, you cannot write A minus lambda. Doesn't make sense. You have to make it a matrix. To make it a matrix, it's going to be lambda times I. Remember the identity matrix times that by K equal to, okay, equal to the 0. Okay, so basically the K that you want to find must satisfy this condition. Okay, this condition, this would be used later on to find the K. Now, in order to find the K, there is a, you know, that is going to be a matrix. If you want to find the lambda to be non-zero, you must make sure that this matrix A minus lambda I is not invertible. And the linear algebra is not going to be invertible if the determinant of this matrix is 0. So this is going to be the one. So we're just using that fact. In order to find the K, okay, in order to find, okay, a non-zero vector K, we must have, or one must have, the fact that the determinant of this matrix A minus lambda I must be equal to the 0. Because if it's going to be a non-zero in the language of the linear algebra, A minus lambda I would be invertible, then K would be 0. But the K is non-zero, it's not 0, so the condition that we impose is the fact that this determinant is going to be equal to the 0. Now, when you form it, you put them together, this is going to be a polynomial. In this case, a quadratic equation. It's going to be a quadratic equation in terms of the lambda because the A and the, okay, A and the I are given to you. Then you solve that quadratic equation to get the lambda. A quadratic equation would have 3 cases. You may get, it's like the one that we did before. Okay, it's a characteristic equation, so you may have real solutions, you may have a repeated solution, or you may have complex solutions. So 3 different cases, and you have to investigate all the 3 cases. So we are going to just, let's give you, let's finish it. So there you are, this star, or the double star, if you like, call it a star. So this star is just a characteristic equation, as we did it before, it's called, okay, the characteristic equation. Okay, this is going to be your characteristic equation of a matrix A. Okay, again, it's a quadratic equation. It is a quadratic equation in lambda. So the eigenvalues lambda are going to be solution of this equation, or the roots, okay, of a star equation. Then as soon as you find the lambda, then you come back and find the K. Okay, and so to find an eigenvector K corresponding to the, well, it's clear, okay, I just explained it. Corresponding to the lambda, we are going to solve this equation. The equation is going to be A minus lambda I times K equal to the 0. I'm going to give you a couple of examples to get this one, and then we move on. I'll give you a break. So we come back and we have to practice this one first. As soon as you're done, we are ready for the differential equation. Okay, so let's have a break. We come back and do a couple of examples on this one, and then we go to the differential equation. We are going to consider only one case for this test. The case that we have the value of the lambdas are going to be different. There's going to be real solution with distinct lambdas, lambda 1, lambda 2. And after your test, we talk about the complex one and the repeated one, which takes time. Those numbers. Okay, so let's have a break for 10 minutes and then we continue.
Better than Mark. No, Python. What's up? No, Python. Yeah, it's a Python. Yeah, my other one didn't. Oh, Tim, alright, why'd you get this one? It's free? Not free, but like, yeah, financial aid, I like $250 every month. My brother has a Python one, so the standard one. Run out. My brother got it, not knowing, and he used it afterwards. The only thing I want to do is why on here. Are you saying you can have probably? Yeah. Like a standard run from Zoom. Standard one? Yeah, like if you download it, you can get Doom on Are they has enough processing power to yeah, but like the graphics are they like oh it's chat. Yeah, don't okay. It would be and like it's really like standard Doom like yeah, very pixelated. So it's like just running down hallways. Yeah, that's crazy. He sped around through. The only thing he forgot were like vector spaces and bases. Yeah, but that's literally those are the things I did it for. So wild. I'm gonna contain all of it. Job on this whole thing. It's the conversation later out for yeah, like the key points to wild. Yeah. I mean, yeah, the rest is not consistent equation instead of differential. You mean you have one number wrong in your calculator, you'll get the answer wrong, but you'll never know you got it wrong. Especially, maybe after the fine, you're more difficult. But once you move on from that, they just do what you call the calculator. And like each time you can have multiple
Okay. If we give you example, how going to find this eigenvalues and eigenvector. So this is going to be, then you change it to the differential equation. So example. So we want to find the eigenvalues and eigenvector of this matrix. Okay, find the eigen. Okay, eigenvalues and corresponding eigenvectors. Eigenvectors of this matrix, A equal to, you have a 3, 4, -1, and 7. That's it. So you have to solve this equation, okay? So solution. So you have to solve the equation determinant of the A minus lambda I equal to the 0 to get the, okay, to get the lambdas. So this is going to be A, this is the first one I explained it. A minus lambda I is going to be equal to, A is 3, 4, -1, 7, minus the lambda, I is 1, 0, 0, 1. Okay, if you multiply the lambda inside, so 3, 4, -1, 7. Okay, it's going to be kind of a plus. You get the negative lambda 0, 0, negative lambda. So if you add them together, it's going to be of this form: 3 minus lambda addition 4, and this is going to be -1 plus 0, and that gives you 7 minus lambda. Okay, so I just did this one. So for the future, as soon as we get the matrix, so A minus lambda I would do simply 3 minus lambda 4, -1, 7 minus lambda I. Okay. So on the main diagonal, we are going to have it. We take out the lambda. Okay, now we find the matrix determinant. So the depth of A minus lambda I is going to be equal to determinant of this matrix, 3 minus lambda 4, -1, 7 minus lambda. Remember, kind of cross multiplication type. So multiply these two together. That give you 3 minus lambda times 7 minus lambda minus. We multiply these two together. Okay, multiply the 4 times -1. You simplify it, then you let it equal to the 0. So we have to FOIL this one. So it's going to be equal to 3 times 7, 21, minus 3 lambda. You go inside, minus 7 lambda plus lambda squared. And negative would be positive, plus 4. Simplify it, write it down in the, okay, in the form of the quadratic equation. So it's going to be lambda squared, -3, -7, that give you -10 lambda, and then 25. So that would be the determinant of the A minus lambda I. You let it equal to the 0. Okay. So you have to solve this equation. And that's easy to solve, because that would be lambda minus 5 times lambda minus 5 squared equal to the 0. So we have two values for the lambda, but they are the same. So it's going to be lambda 1 equal to the lambda 2 equal to the 5. So we have so-called a repeated eigenvalues. Okay, so lambda equal to the 5, if you like, is a repeated, okay, repeated eigenvalue. Later on, you will see that this is a bad case when we get differential equation. It takes time to solve that differential equation. But for the time being, we just checking as a matrix, not a differential equation. Okay, any question? So this is eigenvalues. You have to find the eigenvectors. Okay, so the second part, to find the eigenvector. Eigenvector, remember K, such that this is how we find the K. A minus lambda I times K, you let it to be equal to the 0. Go back to whatever you did before, A minus lambda I. You change your lambda equal to the 5, and then you form this equation to get the K. Okay, remember K is a vector. So we assume the K to be usually, okay, there you are. Assume K to be this vector, K1 and K2. And remember your lambda is 5. So you put the 5 here. Okay, this is it. You put the 5 here. And you form this equation. Okay, so basically this is what would happen. So that was 3 minus lambda, 3 minus 5, 4, -1, 7 minus 5. That is your A minus lambda I, times it by K, which is a K1, K2 equal to the 0 vector. So multiply them together, simplify first. So if you simplify that, give you -2, 4. Okay, that would be -1, 2 times the vector K1, K2, and this is equal to the 0, 0. We multiply together, as we did it before, -2 K1 plus 4 K2, -2 K1 plus 4 K2. And you repeat it for this column, -1, 2, so it gives you -K1 plus 2 K2. This must be equal to the 0, 0. So you put them, you know that we talk about it, two metrics are going to be equal to each other if their corresponding integers are going to be the same. When you write it down, you get only one equation. It's two equations, but both of them are the same. So your system will be dependent and you get infinity many solutions all the time. And we get to know it, we summarize this. Okay, write it down, then I go to the next page. Find this. Any question? Just, doing the algebra of this part. So let each to be equal to the 0 to get a system of equation, and you'll be able to find your K1 and the K2. Okay, so this is going to be, if you let them to be equal to the 0, so we get this equation. You see it's a -2 K1, the first one, -2 K1 plus 4 K2 equal to the 0. And the second one is a -K1 plus 2 K2 equal to the 0. Both equations are the same because this is a dependent system. If you multiply the second one by 2, you get exactly the first one. So this system is dependent and you don't have to consider both of them. You just consider one of this equation. It doesn't matter which one is it because both of them are the same. Okay, so the system is dependent. I consider the second one. So from this one, I consider -K1 plus 2 K2 to be equal to the 0. And I saw for K1, so K1 would be equal to the 2 K2. You see, the system would give you infinite many solutions. You need only one of them. So you pick anything you like, okay, for K2 to get one solution. So for example, if K2 is equal to 1, then K1 is going to be equal to 2. It doesn't matter whichever you pick. because the solutions are going to be multiple of each other. Okay, so the K that we pick for this one is 2, 1. So this is going to be is an eigen vector. Correspond to the lambda equal to 5. If you would like to have all of them, you can pick the K2 equal to the T and the K1 is 2T. That would be something in linear algebra. We consider the linear space spanned by. So we are not interested. Yes.
So the solutions are going to be column vector.
This, yeah, it's a vector. It's a vector, but we denote it by a column vector. Okay, for the sake of the multiplication. So this is going to be your job in order to find the eigenvalues and the eigenvectors. We don't need anything else really. There are quite a lot to talk about it, these type of concepts. Okay, any question? We're done with the algebra. So we are ready to go to the differential equation. So a differential equation will be given to you. The way we're going to do it, we consider the homogeneous one first. We change it to the matrix form. The matrix form would be x prime equal to the ax. We show that if you want to solve that one, it's the same as you did before. The solutions are going to be the type of e to the rt. We call it lambda t. And we have something similar to whatever we did for the linear case at the beginning. Okay, so I'm going to design it and then we are going to do it. Okay, as you can see, it's it's a very nice mathematical modeling that you change from one system to the other one and then you connect them together. From this point of view, this is going to be interesting one. Okay, so this is your job. That was the preliminaries. Now how are we going to solve homogeneous linear system first? Then we go to the non-homogeneous, like the one we did before. So there you are, homogeneous. Okay, homogeneous linear systems of differential equations, of course, with constant coefficient, exactly the way we did it for the equations, with constant coefficients. This system cannot be used if you don't have a constant coefficient. Okay, just copy the system that the method that we did before. Okay, let's do it. Take a system, change it to the matrix form. The matrix form is going to be a linear equation of the first order. Go back, whatever you did before, repeat it again. Okay, there you are. Suppose a system is given to you. That's homogeneous. Suppose this is it, dx dt equal to the ax plus by dy dt is equal to the cx plus dy. This is a system, there is no extra term, so it's homogeneous. Okay, is a homogeneous. Okay, homogeneous system. Okay, system of linear equation. Homogeneous system of differential equation, of linear differential equation with constant coefficient, of course, with constant coefficients which are A, B, C, and D. That's it. Change the system into the matrix form. Okay. So the matrix form, we already talked about it, so we can do it quickly. The matrix form of the system is, remember, x prime equal to the A times x. where A is the matrix of the coefficient. Where A, remember, is the matrix of the coefficient. A, B, C, D. And we already denote the other one, you know what does it mean for the X and X of T. Okay, so this is going to be the case that we have. Now we are going to focus on this one. It's a linear equation. We know the solution of the linear equation. It's going to be of the form of e to the what? E to the RT. We talked about it before, but we have to change it to the matrix form. So we force the equation to be as we did it before. Suppose X equal to the K is vector K, remember. K e to the lambda T is the solution of the system of this of the system to emphasize that where K of course is a vector. K is equal to the K1, K2 is a solution vector. We call it a solution vector. Solution vector. Okay, now as we did it before. Yes.
Is that exponent T and
No, lambda T. Eigenvalues. Lambda. Okay, that's it. So if this is going to be the solution of the equation, it must satisfy the equation. Okay. So that's it. Then there you are. Your X is K e to the lambda T. Differentiate it. X prime. What's X prime? It's like, you know, lambda. You bring it's going to be K as a vector, lambda e to the lambda T. That's X prime. So it must satisfy the equation. So substituting the equation. So what's going to be the result? Substitute here. So the result would be X prime is a K lambda e to the lambda T equal to the A times X. Okay, A times X, A times, what is the X? X is K e to the lambda T. Exponential function is never zero. So we can cancel it out. Okay, e to the lambda T is never zero. Drop it. So what's going to be the result? The result is going to be lambda, okay, K lambda equal to the AK. So X would be a solution of a system. It satisfies this. Move everything to one side. Okay. So this is the way I'm going to move it. I rewrite it as AK minus lambda K, if you like. AK minus lambda K equal to the 0. Factor out the K. So this would be A minus lambda I times K equal to the 0. You see? We arrive at the fact that the e to the lambda T is going to be a solution of a system if lambda satisfies this equation. And you know that this equation is what? This is a characteristic equation correspond to the, okay, that matrix that we have. Okay, so we know the rest. In order to satisfy this one, you have to force the matrix A minus lambda I to be a singular matrix, we call it, non-variables, okay? So this is going to be the case so far. Let me just explain. Any question? I want to go to the next page, continue. So I'm going to call this one equation number 1, because I want to refer to it. So far, what we did is going to be that, so this is it. Therefore, exactly as we did it at the beginning of the course for the linear equation. Therefore, X equal to the K e to the lambda T is the solution of the system. Solution of the system if it satisfies the equation number 1. Okay, if one or we can, if one can find, okay, a non-zero, if you like, vector, K satisfying the equation number 1. Okay, equation number 1, which is A minus lambda I times K equal to the 0. Equivalently, okay, equivalently, one should have, okay, must have the determinant of the A minus lambda I to be equal to the 0. And that's exactly, we know what you are talking about. So which is the same as lambda must be a characteristic. So lambda must be, okay, an eigenvalues, an eigenvalue of the matrix, okay, of the matrix A with the corresponding okay, eigenvector K. Okay, so we know the situation we're going to have. There are 3 possibilities for solving this equation. Okay, so there are 3 possibilities as we did it before. I'm going to talk about one of them only tonight. One distinct solution. We solve this equation, characteristic equation, and we get 2 real solutions. So distinct real eigenvalues, real eigenvalues. So as we did before, remember we call it R1 and R2, e to the R1t plus e to the R1, R2t was the solution of the equation. It's the same thing. So there you are. If you solve this characteristic equation, you get 2 solutions. So if lambda 1 and lambda 2 are going to be R2 distinct real real eigenvalues of the matrix of the matrix A with the corresponding corresponding eigenvectors K1 and K2. They are uppercase K1 and K2. Okay, K1 and K2. Okay, then the solution of the system X is equal to C1 K1 e to the lambda 1t plus C2 K2 e to the lambda 2t is going to be the general solution of the system. Okay, is the general solution of the system. And you're done. So this would be case 1. Case 2 is the complex one. There's going to be just a formula that is related to the complex numbers. make it a little bit more involved. But the tricky one is when you get repeated solution. If you get a repeated solution, the format of the solution will be different. It's like the ordinary one they did it. Remember, if you have a repeated solution for the linear case, one of the solution was e to the RT or Rx, the other one was T times. You have a similar one here, and you got to be careful to get that vector. Okay, so this is where we're going to give you the first test. Okay, so that we give you enough time to practice on Wednesday, the one that I've already posted for you. After your test, we give you the other two cases and the non-homogeneous one for the final. Okay, any question? So easy format, just form the matrix one. Okay, everything depends on that matrix. It's all linear algebra. We find the eigenvalues, eigenvector, put them together, you get the real solution and get that. So let's practice quickly. Make sure we get the numbers. Okay, so that's it. Solve the system. Example. So solve the system. Solve the system. And this is going to be the system. You have the dx dt equal to 2x plus 3y. And you have the dy dt equal to 2x plus y. You want to solve the system. We're going to introduce the a and introduce the x, change it into the matrix form. The standard notation, solution. Okay, suppose A. What's going to be A? 2, 3, 2, 1. That's A. And you introduce the X. X is going to be X and Y. Then quickly we find out, what's going on. And then you have this system, X prime equal to the A times X. Now we are ready. We know how to do it. So we have to find the eigenvalues of this matrix and we continue because everything is already proved. Okay. So go for eigenvalues. We have to form the determinant of this matrix. Determinant of A minus lambda I is going to be equal to determinant of this matrix. We take the lambda out of the diagonal. It's going to be 2 minus lambda, 3. And that's going to be 2, 1 minus lambda. Cross multiply. So it's going to be 2 minus lambda times 1 minus lambda. Minus 2 times 3, 6. That's the determinant of this matrix. Boil it. Continue. Okay, that's going to be 2 minus 2 lambda minus lambda plus lambda squared minus 6. Combine the like terms, write it down as a differential, as a quadratic equation. So that would be lambda squared minus 3 lambda minus 4. Let it to be equal to the 0. We get the eigenvalues. Easy equation. So lambda minus what? Minus 4 times lambda plus 1. So we get two solutions. You can label it whatever you like. So I label the lambda 1 equal to the negative 1 and the lambda 2 equal to 4. These are your eigenvalues. You have to find the eigenvectors corresponds to each of these eigenvalues. We call it K1 and K2, then you do. Okay, now find the K. So I go with the lambda 1. Lambda 1 equal to negative 1. So we are going to find this vector. So I find the A minus lambda I times K equal to the 0. You go to this part and replace the lambda by -1. Okay, lambda by -1. So you get a matrix this time. 2. Okay, 2 minus -1 and the 3, 2, 1 minus -1. Matrix times K. K1, K2, you get it equal to the 0. 0, 0. Simplify it. Yes.
First, the 2 minus 1, I'm confused. How do we get those numbers?
What are you confused about?
Oh, never mind. Never mind. Figure it out. Sorry.
You combine the lectures. Okay, you got it?
Yeah.
Okay, next. So simplify this one carefully. It's going to be 3, 3, 2, 2. You see the first row and the second row are going to be almost the same. You need only one of them. Okay, if you write, you can write the system, but you don't need all of them. It's a 3K1 plus 3K2 equal to the 0. The second one is 2K1 plus 2K2 equal to the 0. All of them are the same. Just pick one of them. It doesn't matter. Okay, I picked the first one. 3K1 plus 3K2 equal to the 0. We divide by 3. You see, it's a dependent system. Always you get many, many solutions. So K1 equal to the negative K2. Many, many solutions, but you need one of them. Pick, for example, K2 to be equal to 1. Any number would be fine. Then K1 would be -1. So your first vector is going to be -1 and 1. This is the, okay, this is going to be eigenvector corresponds to the lambda equal to the -1. Any question?
Equals 1.
You can pick any number you like. Okay, because it's a dependent system. In linear algebra, we call it T, and we get the T and -T, we factor out the T out, but not in this course, okay? Because we need only one number, and we got it. Okay, we have to repeat it again. For lambda equal to 4. Just repeat the procedure. You put the 4 here and simplify it to get the result. Are you ready? Lambda equal to lambda 2. Lambda 2 equal to the 4. So same thing. You have to put it in this equation, A minus lambda I times K equal to the 0. If you go back and put the lambda equal to the 4 again, so this is the situation we're going to have. It's going to be 2 minus 4, 3. And the 2, 1 minus 4. That equation that we did. And this is going to be K1, K2 again, equal to the 0, 0. Okay, we get back to that characteristic equation again. And we substitute. So that gives us a -2, 3. 2, -3. And that's a K1, K2, 0, 0. Again, you get the same equation. You just get the first one and then you're done. So that gives you 2K1 plus 3K2 equal to the 0. You don't even have to read the second, write the second one really. Because both of them are the same. You can do it if you like, but if you do it on the test, I accept it. You just need one of them. Both of them are the same. So that's a 2K1 equal to the 3K2. Okay, so for one of them, K1 is going to be equal to what? 3/2 of the K2. You get the next number for K2. What's the next number? Okay, two.
Two.
You mean two? Okay, two. Three would be fine, but people. Because we're not going to do anything about it. Okay,
Let's do four.
10,000. So that give you 3/2 times 2. So that give us 3. That's enough. That's nice. So the second vector is okay, 3, 2. There you are. So go back, rewrite it to give us the general solution. So what's going to be the general solution now? You see, this is it. X is equal to, we get the two solutions if you like from these. If you like a different way to write it down. One way to write it down is x1 is equal to your k1. So your k1 was 1, -1, and the lambda was 1. Okay, and then x2 is your k2, 3 and 2, and the lambda was 4. You see, this is one way to do it. Now your general solution, x would be c1 x1 plus c2 x2, like the one that you did before. So in this case, your x would be, that's it. It's going to be c1, 1 -1 e to the t plus c2, 3/2 e to the 4t. It's going to be a general solution of the system, but you have to write the solution of the x and the y. Yes.
I thought lambda one.
Is it -1?
Yeah.
Okay, it's a -1. This is correct. 1 -1 again. Yes. Okay, so this is it. Now the solution in terms of the x and the y is going to be, that the x is going to be the first component and the y is going to be the second one. So you can write it. So the final solution is x of t is equal to the first row. It's going to be what? C1 e to the -t plus 3 C2 e to the 40. You see the x is going to be the top component. There's a C1 e to the -t plus 3 C2 e to the 40. That's what
was on top, and then the one was in the denominator. So like -1, and then one in the bottom.
Which one?
So this one,
Okay,
so -1 was on top. At the bottom.
-1 on the top. It doesn't matter. Both of them are the same, but I changed it. Okay, -1. Because we use the constant at the end, both of them would be the same. But let's, thank you. This is it. Okay. So that gives you x of t, c1 e to the -t plus 3c2 e to the 40. -c1 and the c1 would be the same. Okay, that's the x of t. Then we get y of t. Y of t, the second component, c1 e to the -t plus 2c2 e to the 40. So that gives you the solution of the solution of the system. Okay, if you like, I can write a -c1. It doesn't matter. So that gives you the final answer. And this is the way you are going to write it down. If there is going to be any initial condition, of course, you have to apply the initial condition here. There are some cases that you get the initial condition. It's a straightforward problem. Yes, what's the question?
So the two, I have two questions.
What's the second one?
How did you get 2C2 instead of 3C2
Where's the 3c2?
or Y of T?
Because why we go with the second component?
And then you multiply the bottom by T.
No, you see, x, what was the x? X was x, y. Is a vector. The first component is the first row, x. The second component is the second row, y. No?
Oh, okay.
You see, that's the x. And that's what you have. See if you like, you can put them all together. Then let them to be equal to each other. You see, you can write this one as a one vector. There you are. You see, it's going to be negative C1 e to the negative t plus 3C2 e to the 4t. And the second part is C1 e to the negative t plus 2C2 e to the 4t. So x1. Let me do it in short form to get these numbers. Okay, we did it. That's one.
One more question.
Yes.
How did you get the negative 2k1 plus 3k equals 0, and then 2k1 minus 3k equals 0? So, then,
The equation, you see the equation, look at this one. The other part is 0.
yeah, where do you get the minus 2k1 and 3k2? Is that from the original function?
Yeah.
Which one?
You go to the a minus lambda I. Remember? You go to the, look at this one. You go here.
But the venue's killer, so
You see,
it's the same. Thing.
any lambda you find, you have to go back. Hit it down.
Wait,
Let me close this one.
okay.
I don't want it to